A neutralization reaction is a reaction between an acid and a base, which produces a soluble salt and water. And there's four mechanisms that depend on the strengths of the acids and bases. And here we look at a strong acid reacting with a strong base. And the strong acid and base completely dissociate in an aqueous solution. And getting rid of the spectator ions, we obtain a net ionic equation. And you may be given the concentration of the acid and the base and the volume of the acidic and basic solutions. And from that you'll be able to obtain a number of moles of the acid and base, and therefore the moles of hydronium and hydroxide. And therefore if the acid is in excess, the hydroxides will all get consumed, and you'll have an excess concentration of hydronium in the solution, and therefore the pH is determined by the concentration of the hydronium ions. And if instead the base is in excess, you'll be able to obtain pOH, and then use the following equation to obtain a pH at 25 degrees. And if you have an equimolar solution, then all of the hydronium and hydroxide ions will react, and you have a neutral solution. When a weak acid reacts with a strong base, we get a neutralization reaction, and a negligible amount of the weak acid dissolves compared to the strong base. So when we write the complete ionic equation, we assume that only the base dissociates. Where all of these are in aqueous solution and H2O is a liquid. And eliminating the spectator ions, we have the net ionic equation. And if you're given the initial concentration of the acid and the base, then you can work out the number of moles, and therefore the number of moles of hydroxide. And in this particular case, the weak acid is in excess, so all of the hydroxide reacts, and you're left over with some amount of the weak acid. And the remaining weak acid molecules donate a proton to water to yield hydronium and the conjugate base. And here you'll construct an ice table, and you'll determine the concentration of the weak acid and weak base in a solution from the neutralization reaction, which you start off with here. And then from this you'll be able to work out the equilibrium concentration of hydronium in the solution using the equilibrium expression for the acid dissociation constant. And then you can work out the pH of the solution. And we'll look at the Henderson Hasselbalch equation later on, which is basically taking this step of constructing the ice table. And when you have a weak acid in solution with its conjugate base, you have a buffer solution which has a very stable pH, and we'll look at this in more detail. We determine the net ionic equation for a weak acid reacting with a strong base, and we assume very little of the weak acid dissociates in the solution. So in this case, we look at the strong base being in excess, So therefore all the weak acid gets consumed. So therefore the number of moles of the weak acid is less than the number of moles of the strong base. And we determine the concentration of the hydroxide ions from the leftover number of moles that are left unreacted and the total volume of the solution. And from this we can determine the pOH and then use the following equation, assuming a temperature of 25 degrees, to obtain a pH of the solution, which will be basic. And note that we ignore the contribution of the conjugate base of the weak acid to the pH of the solution, because there's going to be a much less amount compared to hydroxide. We wrote the net ionic equation for the reaction between a weak acid and strong base, and this time we're looking at the equimolar case. We have an equal number of moles of the weak acid and strong base. So therefore all of the acid and base is going to be consumed to yield the conjugate base and water. And the conjugate base then accepts a proton from water to yield the conjugate acid and hydroxide. And from here you can use an ice table and the equilibrium constant for the reaction to find the unknown concentration of hydroxide. And therefore you can find the pOH and then find the pH of the solution at 25 degrees, which will be slightly basic given there's hydroxide in the solution. When a weak base reacts with a strong acid, the strong acid fully ionizes while the base accepts a proton from the acid. And from this complete ionic equation, if we get rid of the spectator ions, we obtain a net ionic equation. And we can write this in an equivalent form, where we add H2O to both sides. And in the case where the weak base is in excess, the acid gets fully consumed. And the remaining base molecules accept a proton from water to yield the conjugate acid and hydroxide. And now we construct an ice table and use the remaining concentration of the base and the conjugate acid left over from the neutralization reaction. And use the base dissociation constant to work out the amount of hydroxide in the solution, and then use that to calculate pOH, and then a pH of the solution can be obtained from the following expression at 25 degrees Celsius. And note that when a weak base and its conjugate acid are present in a solution, a buffer is formed which has a very stable pH. We've determined the net ionic equation for when a weak base reacts with a strong acid. And where the strong acid is in excess, the base gets completely neutralized, and we can obtain the pH of the solution directly from the concentration of hydronium ions. Now note that the conjugate acid can donate a proton to water to yield hydronium plus the conjugate base, where these are in an aqueous solution. But the concentration of hydronium from this reaction is much smaller than that obtained from the dissociation of the strong acid. So therefore this approximation of the pH, ignoring the contribution of the conjugate acid, is accurate. Using the net ionic equation that we derived with the reaction between a weak base and a strong acid, for the case where we have an equimolar concentration of the weak base and strong acid, then all of the base and acid are going to be neutralized, and we're left with the conjugate acid, which donates a proton to water to yield hydronium and a conjugate base that is acid, where these are in aqueous solution. And from here you can use an ice table and the acid dissociation constant to find the unknown concentration of hydronium in the solution, and from that you can find the pH, where the solution will be slightly acidic. When a weak acid and base are mixed, they'll reach an equilibrium state, and we can represent the reaction by the following equation, where the acid donates a proton to the base, and we have the conjugate base of the weak acid and the conjugate acid of the weak base. Now given that strong acids and bases dissolve more, then if the strong acid and base are on the left hand side, then their concentration will increase in the solution and the reaction would shift to the right. And to determine if the solution is acidic or basic, then what you do is obtain a base dissociation constant and the acid dissociation constant. So for example, A minus being a conjugate base would accept a proton from water to yield an acid and hydroxide. And similarly, the conjugate acid would donate a proton to water to yield hydronium and the base. So this reaction would have a base dissociation constant, and this one would have an acid dissociation constant. And a larger base dissociation constant would mean there's more hydroxide in the solution, and more hydronium in the solution for an acid dissociation constant. So therefore, if Kb is greater than Ka, then the pH is greater than 7, and the solution is basic, and vice versa. Find the pH of a solution that's formed by mixing 50 ml of 1.8 molar of hydrofluoric acid, which is a weak acid, with 50 ml of 0.9 molar of sodium hydroxide. So first we'll write the neutralization reaction, which yields a salt and water, where these are in aqueous solution. And ignoring the spectator ions, and assuming little of the acid dissociates compared to the strong base, we obtain the following net ionic equation. And now we calculate the number of moles of the weak acid and a strong base. And therefore the weak acid is in excess, so the concentration of the weak acid in the solution is the difference between the two on the volume of the solution, which is 100 ml. And now the remaining acid reacts with water by donating a proton. So we have the conjugate base and hydronium, where these are in aqueous solution. And now we construct an ice table using the molar concentrations of the weak acid and its conjugate base from the neutralization reaction. So this gets consumed and the products get produced. And we obtain the equilibrium concentrations. And now you can use the equilibrium expression and the approximation that the concentration of hydronium is going to be much less than that of the weak acid. So therefore these cancel and we obtain the following concentration of hydronium. And therefore the pH of the solution is the minus log of this value.